Welcome to Build with Naz. My name is Naz. I am the founder of Rebel and author and maintainer of the Rebel open core repo. It's a bunch of crates that are written in Rust and they're all tied to text user interfaces. I actually end up using quite a bit of Tokio and async in all these crates, and in today's video I wanted to cover cancellation safety. I did another video on some of the common patterns that come up with async Rust and Tokio in a different video, but in this one I just wanted to dedicate it to the topic of cancellation safety. So in order to do that, I wanted to demonstrate it with a couple of examples. Like I wanted to show some ways in which we can induce it and then figure out how to avoid it. But most of the time, the good news is that if you end up using and a lot of these cancellation safety issues show up in the select macro, which races a bunch of features to see which one produces a result or resolves first, and then the other one is dropped. So then the question is, what happens when the other one is dropped? When the other feature that's dropped contains state information in it, then potentially that'll be lost in an unrecoverable manner. So when you're shutting down things, that is probably intended behavior, but when you don't intend to shut down something, then you probably want to avoid that kind of drop. And so most of the things that show up in a Tokio select block, if you're using it from Tokio, chances are they're already cancellation safe. And so that's the good news. So to demonstrate this, let's or to actually show what cancellation safety is and how to sort of recognize it. Let's go through a few examples. I'm just going to do about 2 or 3 examples today, so this shouldn't be that long of a live coding video. So let's get started by creating a new repo for the stream. So here we go. Okay. So one of the first things we're going to do is create a test, and in this test we'll just create 2 futures so that we can see the select macro in action, and then race them against each other, and use this as an opportunity to show cancellation safe version of something and then not cancel safe version of something, and that something is going to be sleep. So before we do that, let's grab a bunch of dependencies that we will need. So this is nothing interesting. It just brings in Tokio, and these are actually necessary because we have we're going to be using these to actually create some fake inputs or streams that we're going to use to show cancel on safety. So these will come in handy later on in the video. So the first thing we want to do is create a test. So let's do Tokio test, and we're going to create a test sleep. So we're going to do it both the right and wrong ways, and this is to kind of use a concrete example to demonstrate like what cancellation safety is using something that's not so complicated. We'll do 2 more examples, and the last example is going to be a little bit more complicated than, it's quite actually not that much more complicated, but more complicated than this. So let's do this. We're creating a sleep, and this is std time duration. And what we're going to do is we are going to create a counter. So the thinking here is that we're going to have a loop, because that's the setup basically for these are the kind of things that you look for when you're thinking about cancellation safety. And then we're going to make 2 branches. So we're going to make branch 1. This is the right way, and we're going to do branch 2. This is the wrong way. It's not really the right or the wrong way, but that's what we're going to call it for now. So the right way, actually let's do the wrong way first. So we're going to do Tokio, the same thing actually, times sleep. And what we're going to do here is when this happens, we're just going to print sleep. So this is what this is, and this got rid of the compiler warnings. So essentially what this does is that if we run the test, it'll basically create this future, and then it'll race the future. It will just run this future until it goes to completion, and there's going to be a delay from when this future was started of let's say 100 milliseconds, and then we will see sleep. So if we run this test, we just we get a bunch of warnings. Oh, it doesn't. Oh, it actually doesn't break. So what we have to do is this, and then this will complain because, yeah, okay. So we can actually run this because this doesn't break out of the loop. So let's do this. So at least our understanding of this branch so far is that when the Tokio select macro is expanded, it turns this into a future, and then it races and then runs this future, and which is fine. So let's do another variation of this. So instead of doing, oops, let's do this. Let's do Tokio pin sleep. So this is from the docs. It actually says in the docs, if you look at the, there's the pin one. It's in here somewhere. Yeah, this one. So if you basically well, I'll show you what this does in a minute. So let's do ampersand mute sleep. Okay, so let's do this. Println take, and we're gonna do count. So this is decrement the count, and if the count is 0, we're gonna break out of the loop. Okay. So let's see what the heck is going on here. So this is the pinned, you can think of it as like the pinned sleep. So we're creating a sleep object. So this one, if we look inside, oops, not that one, this one. This returns a sleep struct, and so we save that sleep struct, we assign it to this variable, and then we basically we call this macro Tokio pin, and we'll basically pin this this struct so that it's not going to move. And whenever we see things like this, it's because when the an async function gets turned into a state machine, when the compiler desugars it, there's a lot of state information that's encoded in that state machine, because whenever you hit an await block, that future can return. And when it's resumed from that await point forwards. And so all this information needs to be stored somewhere. So these features are stateful. So the in this particular loop, we have the select macro that's going to raise 2 futures. And one future has the sleep variable, which is pinned to the heap. And we know that it's not going anywhere, meaning that no matter how many times this branch is run and it's dropped and then rerun again and dropped again, we know that this particular sleep variable is going to be stable in the heap. So that's kind of like, because we don't know how, I mean, from the perspective of the select macro, it doesn't know how what's going to happen inside of this in this branch, and how long this particular branch will run and potentially rerun. So it kind of looks at it like that. So the sleep variable is pinned to the heap, and we know that it's whatever we assign to it, that struct is going to be in the heap no matter how many times this thing is started and restarted. So that's one branch. And then this other branch is a little bit different. Here we do, I mean, what looks like the same thing, where we create a call to sleep for the same exact duration, which is 100 milliseconds, and then we once you know that resolves, we just when it's ready, we just print sleep, and then that ends the branch, and then it loops again. So essentially, what's the difference between these two? I mean, even if you discount this this little, I have this exit for, I won't let this branch run more than looks like 5 times. And so even without that, like even if we ignore this portion, they look pretty similar. And but there is actually a very subtle difference, and that is that, let's say that this thing runs 5 times, which, you know, the count is 5. So the first iteration of this and this is looping. So let's say this sleep thing got created, it got pinned, and then the loop got started, and then now it's going to infinitely loop until something breaks. So it starts up, it looks at this future, it essentially creates this future and that future, and then runs them to see which one is going to finish first. And what ends up happening is that this is non-deterministic, because at the point at which this future is created, it waits for 100 milliseconds from that point until it resolves, and when it resolves, it'll print sleep. Now, if this other branch finishes first, then this branch will actually never, it won't run, and what'll happen is its future, this entire thing, because this actually returns a future, because note that whatever future it returns, we pinned it to this variable called sleep. So that's this whole expression right here is this the same expression. It's just that one is pinned and the other one is not pinned. So because it's not pinned, this expression is going to end up being created every single time that this macro ends up arriving at this branch and running it. So let's say the first time we're doing this branch is created, this one is created, and they're both raced against each other. So the first branch 1, is going to end up using this pinned value of sleep, which is started up there, and then when that is ready, this branch will execute, and when it executes, this other branch gets dropped. So when this branch gets dropped, the next time this loop starts up, this sleep has been trashed, it got dropped. So the sleep, the timer starts again for this branch from scratch, because a new instance of this is created. So the second time in the loop, if this finishes first, this one gets dropped, and then because remember, futures they don't actually do anything until the executor runs them to completion. So the executor is the one the future is just a data structure, and so the work is actually done by the executor, and the future just encodes some state information. And so that's why futures are cheap to create. They don't do anything until you call .await on them. That's when the executor runs them until, you know, their next await point. So in this case, the difference between these two loops is that this sleep struct gets created once and it's reused. This ampersand mute sleep, that's what that is, by the select macro. And this one is not. So when this branch, if this branch completes first, this entire struct gets dropped. This does not. This struct is retained throughout the entire life of this loop, because we keep reusing the same pinned sleep struct. This is cancel safe, this is not. So that's essentially what that means, is that if this, let's say, you know, we've done like the 4th iteration and the 5th iteration happens, and this particular branch wins, and it goes, okay, my count is 0, so I'm going to break out of this whole loop, then this gets dropped. So if there was something happening here, if this branch 2 had an allocation to a vec or a buffer of some kind, and it was accumulating things inside of this buffer, and then this branch finishes before this branch does, then whatever information data is in that buffer will end up being dropped, and we won't be able to get to it again. And this could be desirable or undesirable. So if there's an exit condition where we're like, okay, the whole system is shutting down, then it's fine. Even if some data gets dropped, more than likely we were shutting down anyway, and we didn't have anything to do with that data. And this data could come from, like, you know, and in one of the examples later on in the stream, I'll use an async an async stream to demonstrate this, where how exactly the data gets dropped and what are the consequences of that. But at a high level, this relatively simple example kind of points out the sort of the caveats or the pitfalls of cancel safety, where every time a particular branch is executed, whatever expression is here will get possibly recreated, and so whatever state it encodes in there will probably be dropped if any other branch wins before it. And if you're putting buffers and such inside of this particular branch, then that's something to be wary of. So let's see, let's run this thing and see what the runtime behavior is. But this is kind of like what we expect is going to happen, where because this sleep variable is pinned, it's deterministic. It's wait, oops, sorry, this is the wrong comments. So basically, the same sleep future is reused on each iteration of this loop, whereas here the sleep feature is not pinned and it's dropped when the other branch is executed. So whenever this wins, it gets dropped, and then on the next iteration, a whole brand new future gets created, and so it kind of loses track of time basically. So because it's supposed to sleep for 100 milliseconds. So if we run it, notice that so the way this example is set up is that branch number 2, so we can say branch 2, and this one is branch 1. If we run this again, notice that branch 2 got an opportunity to run only once, and it looks like branch 1 wins almost every time except for the first time. And let's run it again. If we run this a couple of times, you'll, even though it's looking like it's stable right now, notice branch 2 never ran. This one is only branch 1. So, and sometimes branch 2 might run more than once. Like, it's non-deterministic. We don't know, and that's the sort of implications at runtime of having this particular expression being evaluated and created and then dropped, and then reevaluated and recreated the next iteration through the loop. And if this branch doesn't win out and this branch wins out, then when this gets dropped, this entire thing gets reset. And in this case, it's not that big of a deal, but what we're losing here, the state information which is what we're losing, is this can no longer function as a timer, as a thing that can sleep reliably for a certain amount of time, because there's too many complications depending on what happened with this branch. It may be recreated, so we don't know when it's gonna actually finish. So this is a very kind of simplistic example of cancellation safety and unsafety. So let me save this real quick to the repo, because I actually like this output a little bit better. I'm going to publish all the code in this example to a repo in the Rust Scratch. I'll put a link to this in the video description later. Okay, so hopefully this is starting to make sense, where like cancellation safety is tied to state information encoded inside of a future, and futures are stateful. So if those stateful futures get dropped, any state that's inside of them also gets dropped. And so there's certain intuitions that might not be forming exactly right, because maybe this is what we think happens implicitly, but actually doesn't. So to kind of make this more concrete, let's use a different example, where here we're going to, because this is non-deterministic. So what if we wanted to do an example which was deterministic? So where the behavior that I want to create in this particular example is that I want to use this same sleep struct, and I want to essentially wait for 100 milliseconds, print a message, and once 5 of these messages have been printed, I want to reliably exit this loop. So and I want that to work every single time. Like, I don't want that to have this flaky behavior, which this code has. So how would we do that? So let's say, and this is going to be safe. Cancel example. So here we can do something very similar to the other ones, where, you know, this kind of like boilerplate, where we just grab these lines here, and then we can say, let's also create a I'm going to create a MPSC channel, and I'm going to use this channel to why is it winding? Oh, and I'm going to use this channel in order to signal a shutdown. So this is going to be our shutdown channel. This is kind of a pretty common pattern in a lot of these select in infinite loops, or these event loops where Tokio select is involved. So another thing I'm going to do is I'm going to create a vec, and this vec is just going to be a vec of usizes, and I am going to use this vec to actually accumulate the output, just so that I can see how many times this loop is executed. So I do my loop. I don't know what happened there. Okay, that was weird. Do my loop. I think Visual Code, VSCode Insiders was not doing so well with that. So here I'm going to put a Tokio select macro block. Nothing really interesting so far. I mean, this is going to be very similar to the other one where we had this ampersand mute sleep. So here we're going to say, okay, so we have a block for this, and then we're going to have a block for the receiver. So, and here we're going to basically shut down, and then let's see, why is this complaining? Oh, right, it doesn't know what it's going to be in the channel. So here we're going to do so basically this one is that stable sleep struct. So this one is ampersand mute sleep. This is how you know it's pinned. So this is going to wait for 100 milliseconds, and when 100 milliseconds elapses, this branch will run, and then essentially that's being erased. This future is being erased against that future, and then this one, this future basically, whenever the receiver gets something in this channel, then this branch will run. So, and by the way, you might be wondering, well, what about cancellation safety? Well, if this, let's say the sleep, 100 milliseconds passes, and this is ready, and this branch runs, does that get dropped? Yes, it does get dropped. And is it okay that it got dropped? Yes. And the reason is because this is kind of like what I was talking about earlier, is that Tokio has done a really good job making almost everything you would conceivably use inside of this Tokio select macro. Almost everything is cancel safe, as long as you use the Tokio versions, like even async read, async write text, TCP listeners, and all kinds of stuff, and all kinds of streams. So this is pretty amazing. This is what makes it a very easy to use, kind of reliable macro to use. The situations where you have to be concerned about cancellation safety is if you're doing something totally on your own and you're maintaining your own buffers, or sort of like intermediate states, which you cannot, it would be undesirable for you to drop them in case one of your futures got dropped in one of these branches. And I'll give an example of that. So let's finish up this loop. So here we have, okay, so this is the this is the this is going to be running at least 5 times, and so every time it runs, I'm going to say, let's see, tick. I'm going to do count, and then I'm going to say, so here, note we have a vec here, and this vec is outside of this loop. So what I'm going to do is every time this, oh, is that right? Nope. Almost right. This one. So every time this branch runs, I'm gonna take whatever the value of count is, and I'm gonna push it into the vec. And then we do want to do a -1, but this actually there's a better way to do this, which is saturating sub, which is count, and this will essentially make sure that saturating sub. This will make sure that it will never go negative, otherwise, because it's a U size. Yeah, count is a U size, this one. So saturating sub decrements it, and then if it's 0, well, I won't break. What I'm going to do is I am going to send a unit type, an instance of unit type, to this channel and get out of this branch. So this branch terminates, and then the loop runs again. Tokio will then race this future and that future, and during this iteration, because this thing has already sent, there's something on the channel, and because it's cancel safe, even though this was dropped when this was sent, it was fine, because this never ran, because it got dropped. The next time this loop runs, this will not run first. This will run first, because this is ready already, because this is cancel safe. So you might have already been using cancellation safety without even knowing it, because if you ever have things like the broadcast receivers, MPSC receivers, and so on, they're all cancellation safe. So are most of these async read and write traits, anything that has async read and write streams, and so on. So and even yeah, so this is pretty awesome. And so note that these are not cancel safe. So if you're using these, maybe take a look. And one kind of, nice thing you could do is just document cancel safety in any functions that you write, which may have cancellation safety implications. So here, at the end of this loop, what do we expect to be true? What is going to be in this vec thing? I think this is what's going to be in the vec thing, where because no matter how many times I run this thing, I expect that it's going to be safe. It's going to be consistent. Like, it's not going to be flaky like the other one. Oops, this is Tokio test, not Tokio main. So here, if we run it, let's see what happens. So we go. Actually, let me put like this. Let's call this branch 1. Branch 1, and let's call this branch 2, and here we can say branch 1, and here we can say branch 2. All right, there we go. Nope, I broke it. What happened? Didn't, what? What did I change? Let's see. Let's undo this. Must have broken something. That's weird. I just added comments? How did this break the code? Alright, let's see if this runs. Oh. What happened before? It was Tokio test. I think it was Tokio main before. What the heck? Tokio pin. It's like, does this not count as 0? So we start count at 5. We decrement count. Let's see. Channel of size 1. Okay, tick, we push it, we decrement count, and then we say if count is 0, then exit. And that just breaks. Yeah, that should work. And then we have an assertion at the end saying, okay, let's just see that even. Okay, that's just weird. Let me see if I messed up my typing. Let's do this again. Okay, I have no idea what I did wrong there, but let's see. This is going to be branch 1. This is going to be branch 2. Here we're going to say branch 1. There's our thing, and here we're going to say branch 2. All right, there we go. So here you can see branch 1 runs, tick is 5, then 100 milliseconds passes, tick is 4. But every time this is happening, it's actually evaluating the both of these branches. So it just so happens that branch 1 is consistently running because the nobody sent not sent anything on the channel, on the FBSC channel. So only when this branch 1 executes and tick is 1, or count is 1, I should say. Tick, let's say count, let's say tick, and then count equals. And then when count is 1, only at that point. What the? Is there something in this print line? What is going on here? That's weird. So we got tick, and then we got count equals. Huh. Interesting. I wonder if there was something with the colons that messed up. I think I had like this first. That just. Nope. That works. I don't know how I don't know how I broke it. I do not know how I broke it. Oh, that's how I broke it. Well, what do you know? That doesn't work. Huh. Interesting. Wonder. Sorry, I'm digressing. This is supposed to be about. Oh, that doesn't work. So colon. This must mean something. Interesting. Must be some print line formatting or something. Well, what do you know? That's why it wasn't working. Oh. Interesting. You know what? Let's just do this. Branch count equals. And then let's see. Oh, that doesn't work either. What the? Okay, let's just do simple. No, that doesn't work either. What is going on? Maybe it's VSCode. Yeah. Maybe I shouldn't be using insiders. Maybe that's what this is. Interesting. So if I use a simple print line, that works. But okay, let's just do this. We're going to just get branch 1 and tick and count equals. What the? Okay, doesn't really want this. All right. So I cannot put equal. Okay, I'm gonna let this go in just a minute. Just wonder why this isn't working. Count equals. Okay, now it works. Okay, whatever. Nope, now it doesn't work. What the? I think it's VS Code. I'm pretty sure it's VS Code. Yeah, something weird is happening. Okay. Yep, it's, let's see. It's not. This makes no sense that this wouldn't work. Huh. Okay, whatever. Yeah, okay, I'm not going to use VS Code Insiders anymore for these videos. Bit late to switch right now to the regular code. I usually have VS Code Insiders and VS Code. VS Code is usually for me working on my production code with the Rebel open core, so just out of convenience I use Code Insiders, but not going to be doing that anymore. I've seen some weird behavior with Code Insiders before. There's an update. Yep, there's an update. I will deal with all this later. Okay, so we have this running, which is great. So that's the consistent version of this code that we did first. The difference is that these are cancel safe now. So that's the key. So let me just save this to the code base. I'm actually copying this to the repo so that the code examples in the repo will match what we see in the live stream. I mean the live coding session. And only problem with IDEs or LSP in general with Rust is that because this is a macro, these tokens don't get formatted. So the indentation can get pretty wonky pretty quickly. Okay, so with that done, okay, so this is definitely some VSCode nonsense. But if I do this, nope, this is so weird. Let's say cargo test. Let's see, test, save, cancel example. Yeah, that works every time. So, nope, that didn't work. What the? Interesting, it seems to have hung up. So if count is 0, saturating sub sends the thing. Wonder if, oh, why am I awaiting this? Oh, because it's an async function. There's another variant of this called try send. Maybe I can. Nope. What the? 0, 0, 0, 0. So it's adding zeros. Interesting. So I need to do this. Interesting. Let's see if this works. Huh. Oh. Interesting. So even after, this is fascinating. So we did 5, 4, 3, 2, 1, and then there were 2 zeros. Interesting. Let's see. Huh. Now there's 3 zeros. So 5, 4, 3, 2, 1, 0, 0, 0. So branch 1 gets executed. So it takes a little bit of time for this doesn't do its thing right away, it looks like. And there's like 100 milliseconds that passes here, here, here. That doesn't make any sense. So if count is, so we should do, okay, so count is this. All right. So it pushes the count. It decrements it. And if count is nothing, it tries to send a unit. And oh, right, because 0 is right, because of that reason. Now what? Left is oh, now it did not include the 0. So the 0 sometimes there, sometimes it's not there. Now there's 2 zeros. Now there's 4 zeros. Now this is actually working the way we want. Interesting. So this is flaky as well. Interesting. I wonder why. So we do sleep for 100 milliseconds, I think. Yeah, sleep time 100 milliseconds, pins it, and then I think that's what was here. Where's that pinning one? Maybe it's one of these racy if conditions. Incorrect usage of sleep with if. The objective is to repeatedly run an async task for 50 milliseconds. However, there's a potential for sleep completion to be missed. Whilst not sleep is elapsed. Tokio select. If sleep is elapsed may return true, even if sleep poll never returned ready. This opens up a potential race condition. Ew. One way to write the above example without the race would be, that's what we did. Yep, that's literally what this is. Ampersand mute sleep with Tokyo pin sleep. And goes operation timed out. Interesting. Maybe what we can do here is maybe, let's see, now is this, yeah, this is non-deterministic because it's producing different results depending on when I run it. So let's see, maybe what we can do, yeah, it failed again. So maybe, looks like sleep is good for like once, like for this to like hit once, not multiple times, it looks like. Maybe what we can do instead is interval. Let's do an interval. And then here we can say interval.tick. And I think we have to make this mutable. Okay, let's see if this does it. Okay, that makes sense. I think I was using interval the wrong way with, I mean, I was using sleep instead of interval. Should have been using interval. Sleep is more like, I think I understand. It's, wow, that's a good example. So let's see. So sleep is more like do the, like wait for a certain amount of time. Once that time elapses, you're done. So this is probably better written with interval as well. Let's see, test sleep right. Wrong ways. Let's run this a few times. Yeah, this one. Okay, this one works, but I mean, technically speaking, because we're sleeping here for, what is it, 5 times, this should really be an interval. So this can be, let's say, let interval like that, and then here we can just get rid of this and say interval.tick, and that has to be mutable. And let's see, that should, yeah, it's still, I mean, it's the same thing. It's still, you know, sometimes there's a sleep, sometimes there is no sleep. Looks like mostly here there's no sleep. But I think I'm pretty sure I saw sleep here. Or maybe I didn't. Okay, sleep right in wrong ways. 1 1 1 1 1. Okay, that's just branch 1. Ah, branch 2 sleep. Yeah, so it is non-deterministic. That makes sense. Okay. That makes sense. So we could do this. Oh, this is, let's see, I guess if we run it a lot more times, seems to be pretty stable so far, but I know that I saw the sleep, so maybe what we can do is make a v1 and a v2 of these things, and then one with interval and one without. So here we can do, this is the sleep version where we pin it and we just use this, and here we can have v2, which is using the let's see, did we use interval there? No, here we're going to use the interval, and let's see, this one looks like tick. Branch 2 never gets a chance to run. Although we did see it once. Ah, there we go. So yeah, same thing. Okay, so these are equivalent. So I can say this is equivalent to test sleep right and wrong ways v2, and this is equivalent to v1. This example, this test uses the what are we doing? Tokio pin sleep, and this example, or I should say this test, uses interval. Interval. Oops, Tokyo time interval. Yeah. Okay, so this one uses Tokyo pin macro. Is that not? No? Oh. These would have to be inside. Okay, so that uses Tokyo pin and sleep. Okay, that works. And this one uses interval. So yeah, did not, that's kind of an interesting little discovery. So yeah, sleep, this is using pin sleep, and this is using an interval instead of that, and their behavior is very similar. And here, because of the like what we were intending to do, which is like have an interval, basically a 100 millisecond interval, and then wait for 100 milliseconds, do something, wait for 100 milliseconds, do something, and repeat until 5 of those have passed. This makes sense. All right. Whew. All right. So that was, this is fun stuff. Let's see, test, safe. Here's the difference between it should work and then you run it and then see actually what happens. It's like just because it compiled doesn't necessarily mean that it's gonna do what you think. And yeah, it's too bad. I thought that it was some VSCode thing. So what was happening is that these tests wouldn't return, and for some reason this wasn't picking up on the output. So as you can see here, the output is being streamed to standard out immediately as it's happening, and here it's being buffered. Anyway, so that's good to know. So yeah, this is always nice. You can always put a, let me write this here. I'll put this in the docs so that way it'll be easy. So here we can say run the test using like that, and this one right, I can say run the test using, and then this one. I think, I wonder why it's complaining about spelling errors. And then V1. All right. Okay, that's fantastic. Okay, so now, whew, with that out of the way, let's let's go to the final sort of example that I had wanted to show, where we're going to have a async stream and we're going to do something that is not cancel, unsafe, and mess things up on purpose. So because we, most of these cancel, like things like the MPSC receivers and all that kind of stuff, all these things are cancel safe. So I'm going to create a stream which is not cancel safe, just to show, like, what can go wrong. Okay. So for our final example, I'm going to create something that is purposefully cancel unsafe, not safe to cancel. So let's create a, there's a bunch of boilerplate that has to be built in order to create a test fixture that we're going to be using in order to demonstrate the lack of cancel safety. So let's see, this is our, okay, so here, just to kind of cover these things, there's a bunch of dependencies we're going to need that come from this async stream, futures core, and futures util, because I need a way to create a stream, an async stream that we're going to be using. And this async stream is going to be like a mock for a real, like, source of bytes, like a TCP stream or something like that, or maybe reading from a bunch of like a file or something like that. So this type, these are just some imports that we'll need, and then this is the type of the input stream. This is the mock one, and this actually comes from one of my videos, the one I did on polymorphism and I think dynamic and static dispatch, and so yeah, this is, there's a whole video on dynamic dispatch and polymorphism that it was all about, like, how to use like din, some trait, essentially a trait pointer to in testing. So here, this is a trait pointer, basically a pinned and a boxed trait pointer. So let's see. So with that boilerplate out of the way, this is the, and this is also from Rebel Terminal Async project, which has a whole bunch of tests for async stuff. So here we have a function where, let's do this. Let us, okay. So let's say we have a function called getInputVec, and that returns a vec with 4 items in it. And this is essentially what our stream is going to be returning, our async stream. And so we have this function called genInputStream, which uses the stream macro in order to grab each one of these items, and then every time next is called on the object returned by this thing, it will the first time next is called, it'll return 1, the second time 2, and then 3, and then 4, and so on. So that's what this is. So this is a stream macro. This comes from I think this is, where does this come from? This is from async stream create. So okay, so let's see. With these two sort of boilerplatey things out of the way, this is the here's a test to see how this thing works. So we have, and again, this is all from the Rebel Terminal Async, which I've done videos on this before. That's why I'm just copying and pasting from those examples. But we will go through this next one in detail. So this is what this does. It actually, let's run this in here, because I now I like this now. So we go test. There we go. So you can see what it does is that we create a counter, we create a stream. It has it uses a stream macro to just grab, every time next is called, it just grabs something from the vec and returns it. But it also waits for 100 milliseconds. So it's mimicking a very slow stream. So 100 milliseconds every time you hit next, there's going to be a 100 millisecond pause, and then you're going to get a number. So this is what it looks like. We have we go while let some stream.next await. Notice the await. This is very important for what we're about to set up for cancel and safety. Is that we need something. We need a stream, an async stream. So this dot await is very important. So here, what this code does is that it just keeps going until this stream doesn't have anything left in it anymore, and then just compares to see that it gets all the expected values. So that's how this works. So that's pretty straightforward. It's nothing that interesting there. I mean, outside of this type is interesting. Okay, so now we're going to put it all together. So let's say that we have a function, an async function, which reads from this stream. Notice that this stream only returns 4 items. And this function only takes 3 items from this stream, and that's all it does. So and if it finds 3 items, then it returns them in a vec. So we go async function read 3 items, and this is not cancel safe. So this is and the thing that it takes as an input is a pinned input stream, and then it returns a vec of view size. So this is the function that we're going to have to write. And then the way we use it is that we have a Tokio test, and this one is actually just unsafe cancel example. Here we're going to basically use this thing in a select loop. I mean, sorry, in a select macro. And then see it all, not work. So let's do this. What we're going to do is we're going to get our stream. So this is gen input stream. Then we have a sleep time of 100 milliseconds. Oh, sorry, this is 300 milliseconds. So since we know that there's a delay of 100 milliseconds between every call to next, what we're going to do is we're going to drop something before we're done reading all these items from this stream. So this is a bunch of setup. It all makes sense in just a second. So then we have our sleep. So Tokio time sleep, and then the duration is I think from milliseconds, and this is going to be sleep time. So this is our we're going to pin this thing. So we go Tokio pin sleep. There we go. All right. So now that boilerplate is set up, we're going to do our select macro. And here we're going to do 2 branches. So the first branch is just going to be, we're going to take the sleep, and whenever it's ready, we're going to say println time is up and end. And so you can think of this as a timeout. So this branch really behaves as a timeout. So you can think of it as like you're performing some network operation, and you're going to give it 300 milliseconds. After that, if it hasn't completed what it's supposed to do, you're just going to error out, let's just say, or something. So, and within those 300 milliseconds, if it works out, then you're going to say read 3 items, and we're going to pass it this stream. And the stream thing, we've already written a test, right, to see how that works. So we can say got 3 items, and here we go. All right. So here we have 2 branches, and essentially in this one we're going to say branch 1, this is our timeout, and then we have branch 2, this is our read from stream. So these are the two branches, and then here we can say branch 1 time is up, and we can say branch 2 whatever, got 2 items. Okay. And then at the end of this loop, what we're expecting, so let's take a look at this real quick. So we have 300 millisecond timeout. It takes 100 milliseconds every time we hit next. There, we're not going to be able to get 3 items within 300 milliseconds. We'll be able to get at least 2 items. So more than likely, this is going to fail. So we can say, let's see, this is, this basically, it's like, okay, what is it when we call next on stream, what do we get? So we're gonna assert that what we get is 3, because we're gonna say that only 1 and 2 is consumed before the timeout happens. Consumed where? By branch 2 in branch 1. So that's our hypothesis. And so the what happens when, so here's the question. What happens when this is reading, let's say, 2 items, and then the timeout branch activates? It hasn't returned anything yet. It's been accumulating what it's going to return in this function. So what happened is that so this function is not safe. So basic, or cancel safe. So let's implement this. So we say let mute vec. So this is where it's all going to fall apart, because this right there is state that is inside of this future. And when this future gets dropped, the state will get dropped. So I'm kind of giving away the ending. So we go, so we say, we do this 3 times. We say, we get an item from the stream. So stream.next, await, unwrap, and because it's an option that wraps result. And then we say vec push item. There we go. So when we are able to read 3 of these, then we'll be able to fill this buffer, and then we can return it. So, and let's see, there's a stream. Why is this? That's weird, because this is that stream. I don't know what. That's weird. Okay, so I don't know why it's giving this error. Why Clippy is, because clearly it's used here. Okay, that doesn't make any sense. Let's see. Where's Clippy? Let's change this to check for now. Okay, that was a VS Code setting where every time you hit save, it can either use cargo check or cargo Clippy. So clearly cargo Clippy wasn't producing. Because I don't know what's wrong with this. I think I need a new version of the VS Code insiders. Okay, so this is an async function. That means that every time this await point is reached, this can essentially be paused and resumed. So essentially you return from here, and if the executor isn't driving it, then like nothing is happening. So let's walk through this real quick. Actually, let's see if this works first. Okay, let's see if this runs. Okay, let's run it the way we like to run it, using the terminal. Okay, let's do this. Okay, let's put this side by side so we can see what the heck is going on. All right. Oh, why is it running 2 tests? Oh no, this module is called the same. Great. Let's call this test unsafe cancel example, and this one is test unsafe cancel stream, something like that, whatever. Okay, so let's run that again. Okay, so we're running this test. It goes yielding, so it yields, so yield comes from in our gen input stream. Every time it yields an item, we print line yielding event. Actually, it should just be item, and this should be item. Let's run that again. Yeah, so yielding item, and let's see, so where is this? It should be, I think we're calling this item. I'm updating this in the repo as well. Okay, so every time next gets called, we see yielding item 1, yielding item 2. So if we look at this branch, let's match it up with what's happening. So we create a stream that's mutable, and we save a reference to it in this variable. Then we create this sleep, and we pin it. So we've seen all of this before. This is new, but this is we've seen before. Then we have a select macro, which races 2 branches. So one branch is the timeout. So when sleep is finished, it'll just break out of the loop and say, okay, your time is up. Branch number 2 calls this function, which is async. Read 3 items, and it is not cancel safe. And it takes a reference to a mutable stream. So we know that it's actually taking things out of the stream, and we know that there isn't going to be enough time for it to collect all the 3 items that it needs. So the way this function actually works internally is that it gets an item. So it gets 1, then it waits 100 milliseconds, and then it goes, okay, I'm going to push this into the vec. But actually, notice this await point. So it's the first time it hits this 100 millisecond, it gets 1 item. It's waiting, so it yields, and basically we still haven't hit the 300 millisecond delay yet. But it is the future isn't running anymore. It's waiting. So 100 milliseconds passes, then it wakes up again in this loop, and then it gets a second item. Then it waits again. Now, in the meantime, while it's waiting for 100 milliseconds, this branch wakes back up, because remember, these are all the wait points, right? So this one is waiting, this one is waiting, and this line is waiting. So it goes, the first time the loop runs, it's erasing these futures. So it gets, this one is waiting for 300 milliseconds, so it's in a waiting state. It's waiting to be woken up. Then this one goes, this one goes and gets 1 item, but then it's cost 100 milliseconds, and it's waiting again. Now we have 200 milliseconds before the sleep is going to activate. So then it grabs the next item, and then it's going to wait again for 100 milliseconds. While it's waiting, Tokio, the executor, wakes this thing up, and this one goes, okay, time's up, break. And it breaks out of this loop, and it drops this branch, it drops this future. So this vec that had inside of it item 1 and item 2 is now dropped, this vec, because this future is now dropped. So this never returned. However, 1 and 2 have been taken out of the stream. They're no longer in the stream. We've exited our loop, and 1 and 2 are lost. And that is not cancel safe. Oh, I see. So basically, it's yielding because we are calling stream.next. So never mind. It's actually pretty clean. It's way simpler than I was thinking. So basically, let's put some cleaner statements in here. So this is happening in branch 1. Let's see. Let's put some here. So stream.next. This is happening in read 3 items, and let's get an item, got item, and item, and then finally here we can say let's see, loop exited. There we go. That's better. So now there won't be any confusion. I won't confuse myself. So let's put this to the side and see. Okay, so we, oops, what the heck have I done? $1. Where is it? I made a silly mistake. Dollar. Oh boy. I see. Here we go. Okay, that's better. Let's run this real quick. I think I got confused between templates, string literals in a different language. Okay, so yield item. Okay, so we are in, actually it doesn't say what, oh, so we are in, actually we should say, this is entering read 3 items function. All right, so now it will be a little bit easier to read this output. Okay, so you can see right away, we are entering the read 3 items not cancel save function, and it's gotten its what the heck happened there? It's gotten its first item out of the stream, and it hit the await block, so it waited 100 milliseconds. Then it got this one, item 1. Then it says, okay, cool, I got item 1. Then it calls stream.next await again. Then it goes, all right, I got item 2. Then, because now it's at 300 milliseconds, this feature is dropped. So this is no longer running. This is bye-bye. This vec has 2 things inside of it. Actually, why don't we print this here as well? Say println vec so far contains, and we can do vec. How's that? So we can see what's in it so far. So vec so far contains 1, then vec so far contains 1 and 2. Then he goes, okay, branch 1, time is up, let's end. And then it's now dropped this read 3 items not cancel save feature. And because, you know, this returns, because they sync it, when it gets desugared, this returns a feature. And that feature gets dropped. When that feature gets dropped, all the state inside of it gets dropped, and the state inside of it is a vec that so far contains 1 and 2. This has now been dropped. And then what we have here is branch 1. Okay, time is up. That's correct. And actually, this is branch 2. Maybe we can say that. Say branch 2 is like kind of nested deeply inside of branch 2. So this is, there we go, branch 2. Yeah, so branch 2, vec so far contains 1. Then vec so far contains 1 and 2, and now 1 and 2 are lost, because branch 1, this feature finishes first, and and then once this resolves, or this one gets dropped, when this one gets dropped, 1 and 2, that vec gets dropped from this feature. And then we have loop exited, that's right here. And then this is for the test assertion. The reason I got confused by this, it says yielding item 3 is because we say stream.next. And correctly so, stream.next has 3. If we did stream.next again, it would be 4. And then the stream would end. So this is basically how we can invoke things being dropped in which are contained instead of a future when one of the branches actually finishes before the one that has all the state. So obviously one way to fix it would be not to use the vec in here, and we could pin it, we could pass it in, we could use like an actor pattern and do like a channel or something, and then basically generate use a different way of not like consuming everything out of the as we consume things from the stream, instead of like dumping them into here, maybe we can send it over a channel, accumulate them elsewhere. That's an alternative to passing in the vec, which is pinned to this function. There's many ways around it, but I just wanted to show specifically, where it can go sideways and what to look for if you're auditing your code that has Tokio select statements. And I think for the most part, as long as you're sticking with these, it should be fine. Whew, that ended up becoming a much longer video than expected. So let's see. If you like the style of this video, please give me a thumbs up and subscribe to the channel. That way you'll be notified when new content drops. And if you haven't already, please do subscribe to our newsletter, because when you blog content and video content, when I publish it, I usually send out a newsletter. It's not that, it doesn't happen that frequently. And yeah, I have a few more. I'm working on another video right now on Rust lifetimes. Been meaning to do that for a long time. So, and there's a whole bunch of other stuff I have, but that's the next one that I think I'm going to be working on. Thank you so much for watching, and I'll see you in the next one.